Hello, everyone. Welcome to Bold Conjectures with Paras Chopra. Today, I'm with Dr. Chris Fields, who is an information scientist interested in physics, development biology, and cognitive neuroscience. He's a PhD in philosophy from University of Colorado. He has held positions as a professor and has played a key role in the Human Genome Project. Currently, he's an independent scientist. His recent publications include work in the foundation of quantum mechanics, morphology, evolution, and information systems. As you can see, his research spans fields that aren't traditionally overlapping. And that allows him to come up with unique and bold insights, which I've really loved going through when I was reading in his papers. Earlier in the podcast, I interviewed Dr. Michael Levin and Dr. Donald Hoffman, and our today's guest, Dr. Chris Fields. I've collaborated with both of them. I'm excited to build on those previous podcasts and continue in the journey to understand how much we can know about mysteries of reality and consciousness. Welcome, Dr. Fields.
Thank you very much, and thank you for inviting me.
Dr. Fields, I wanted to start with understanding what got you into studying quantum mechanics professionally. I would love to know more about the arc of your career.
Well, my career has been a bit of a random walk through academic space. I was a physics major in undergraduate school with minors in both math and philosophy, with a concentration in logic and 20th century philosophy. And when I went to graduate school, I became an experimental nuclear physicist. So I spent several years doing accelerator work. And that requires a certain kind of intuitive familiarity with quantum theory to understand what you're doing, to understand what the results mean. So I think I started to develop intuitions then when I was doing experimental work. And I migrated from physics to cognitive science and then to biology, and ended up spending my early career in the Human Genome Project doing bioinformatics. So following kind of a stint in the corporate world, my wife and I moved for several years to Costa Rica, and we became travel writers. And then I took up doing science again, and my focus was really on how humans or any intelligent systems, including individual biological cells, interact with their environments, and how, in particular, humans identify objects in the environment and regard them as existing through time.
Right.
Which is an old philosophical question, but it can now be addressed with real science. So it's very interesting.
Yeah, it's interesting. Your career has went from physics to philosophy to biology, back to physics, travel writing, and then now again back to physics. Sort of a meta question before we dive into the main subject. Has it been difficult for you to specialize like traditional academics do, especially now that you are an independent scientist, which is completely outside of academics? Any general sort of insight that you have about yourself in the sense of what made you explore so many different fields?
I think I'm more interested in questions than disciplines. And I find lots of things fascinating. So I certainly have a background that would more or less preclude a standard academic career. Though I hope that the disciplinary barriers in academia are starting to come down, because I do think that most of the interesting big questions that are out there would benefit from many different disciplinary points of view.
Yeah. mean, I personally have loved looking at this phrase independent scientist as your affiliation whenever I'm reading one of your papers, because it's very rare uh, I mean, independent scientists in these days are rare. In the past, when people were doing gentleman science, it was quite common. But today, most of the science happens in academia.
Right. Well, certainly experimental science is extraordinarily expensive. So it requires a strong institutional basis to even be feasible.
Right.
And
right.
The internet, fortunately, has made it possible to do research without being on site in a library and to have colleagues without being in the same building or city or anything else.
Certainly. Fantastic. So, Dr. Fields, coming to the main sort of one of the threads I wanted to explore was this difference between quantum mechanics and classical mechanics. I know you've written about it and you've spoken about it, but I think as a background to a lot that I wanted to get into, perhaps could you explain what essentially is the difference between how we see the world around us, which is classical mechanics, and what's actually happening when we sort of try to deal with quantum mechanics?
Yes, I can launch into that. I'm going to give you what may be a slightly radical view of things, but I think it's correct. And I think that there are certainly people who would agree with me on this, that classical mechanics and quantum mechanics, and I would actually rather use the word quantum theory than quantum mechanics for reasons that will become clear, are two very different kinds of things. Classical mechanics is truly a theory of mechanics. It's about how objects move in space and time, and the forces that act between objects as they move in space and time. And as Nicholas Geisen has emphasized, the idea that forces had to be transmitted between objects in time by some sort of carrier is really a fairly late idea in the history of classical mechanics. And it was an idea that Einstein, of course, insisted on, with the speed of light as a speed limit on the transmission of forces. But in the first 3 centuries of classical mechanics, basically from Galileo to the late 19th century, forces were thought of as instantaneous. So one had this world, if you go back to someone like Laplace, who I think had the clearest vision of classical mechanics that I know of. You had a world of particles moving around, and they were instantaneously affecting each other by various forces. And in Laplace's time, the main force, of course, is gravity, and then soon thereafter we had electromagnetism. So classical mechanics is really about things interacting in space and time, and in its roots, it's about things bouncing off of each other in space and time. So classical mechanics is about billiard balls or cannonballs or whatever. And quantum theory, I think, is very different. And historically, quantum theory was developed to deal with phenomena like the photoelectric effect, that radiation appeared at particular frequencies and not others. It was designed to deal with atomic spectra, where again, you have energy appearing at particular frequencies and not others. And to, of course, deal with atomic and nuclear physics. And the standard picture of an atom looks right like a little solar system. And that is, of course, not correct. This idea that the electrons are moving in trajectories around the nucleus isn't correct. And Bohr said that already in, I believe, his 1913 or 15 or something paper, that this question of mechanical motion simply couldn't arise in this atomic physics setting. So already you have with Bohr this rejection of the very idea of mechanics. And I would say that quantum theory is in fact not about mechanics at all. And I would claim that quantum theory is not actually about motion in space and time. It's not about particles. It's actually about how physical systems exchange information. So in the last 2 decades or so, we've seen many formulations of quantum theory in informational terms, and there's an entire field now of quantum information and quantum computing. And this whole movement in theoretical physics is about giving physics itself an information theoretic basis. And quantum theory is center stage here as a description of how physical systems can exchange classical, if you will, information, can exchange observational outcomes in the language of the theory. So that puts quantum theory in a completely different place than classical mechanics. It's not meant to tell us how things move around in space and time. It's meant to tell us about how systems exchange information. And in particular, it tells us how we, as physical systems, exchange information with our worlds. So people characterize quantum theory as having a measurement problem. I would say quantum theory is, in fact, a theory of measurement. That's what it's about. It's about how physical interaction leads to information exchange.
Right. I mean, in fact, you preempted my next sort of question, which was around measurement problem itself. But I love this characterization of not using the term mechanics at the quantum level, because I mean, from the classical world, our intuitions about objects moving, what you are saying is that there is nothing, I mean, there may not be necessarily a concept of movement as we imagine in classical world, applicable in the quantum, at the quantum scale. I mean, things may not necessarily be moving. I mean, say a spin where, I mean, the prototypical sort of characteristic of matter spin, there is no movement per se happening, but quantum laws apply there.
Right. Yes. Spin is a very good example. If we think of a ball spinning, then obviously there's real rotation. And if we have a ball or a gyroscope or something like that that's spinning up, and we want it to make it spin down, then we have to actually move the thing.
Yeah.
But if one has an electron in some orbital that has a spin of plus a half, and it transitions to another state where its spin is minus a half, then there's nothing that, you're not grabbing something and turning it over.
Yeah.
right? That whole idea of motion is not applicable.
Right. So from an intuition level, automatically these metaphors jump where an electron is spinning on its axis or around the nucleus. I was curious to understand what intuitions do you apply when you want to understand these things? Do you completely eliminate any sort of classical metaphor and you just see these as maybe computer programs exchanging information?
Well, I think it's helpful to try to eliminate as much classical thinking as possible.
But what do you replace it with?
I think a computing kind of metaphor is probably very appropriate. I mean, if you think of electron spins, for example, as just bits that can be flipped, I think that's a more useful way to think about it than as little things spinning around.
Okay.
Now, it's nice to draw little things spinning around, right? Because that really does communicate an intuition to an audience. So, I see no reason not to do that, as long as the message is this isn't really a little soccer ball that's spinning around.
Okay, so you said quantum theory is a theory of systems exchanging information. Can we dive deeper into this? What exactly is information here, and then what exactly is a system?
Well, I think the question of what a system is one of the central questions in quantum theory, or in the meta theory of quantum theory. And I'll tell you how I think about it at any rate. If one is just going to talk about a universe without saying anything about what the systems in it are, then the axioms of quantum theory clearly apply, and they say you have a universe, it's an isolated system, so it's going to evolve through some unitary propagator. So you can think of it as being represented by a vector in some very large Hilbert space. And the vector just sort of sits there and rotates around in various ways. And that's all that's going on. So the system isn't undergoing any measurable state change, right? It's the phase of its vector is rotating, and that's it. So if you want to say something interesting, one has to decompose this system into parts. So the simplest way to decompose it is into two parts. And so now we have the question of how are we going to think about the description of these two parts? And if we assume that the parts are maximally entangled, then the division doesn't mean anything, right? We haven't actually done anything. So if we want to think about parts of a system in a way that allows us to describe the parts, we want the joint state of the two parts to be separable. So we want to be able to say call the parts A and B. We want to be able to say that the state of AB, the whole thing, is a product of the state of A and the state of B. So we want to be able to assign states to the parts. So whenever you say, okay, I'm going to divide a system into parts and I'm going to assign states to the parts, and be able to talk about them independently, then that's an assumption of separability. And that's effectively an assumption that the interaction between the two parts is weak compared to the internal interaction in each of the parts. So that's not a bad assumption to make. You have two things that are interacting, but they're not interacting all that strongly, so that they kind of count as individual objects. So let's think about describing my interaction with everything that's not me, the rest of the world, the rest of my world. I want to be able to think of it as having some state, and I want to be able to think of myself as having some state. So I want to think of the joint state of me and my world as being separable into my state and the world state. And that allows my interaction with the world to exchange information with the world. So I can get information from the world and I can give information to the world. So what does information mean here? It means observational outcomes. So if I'm looking at the world, my world, then I'm seeing various things. I'm seeing a laptop, I'm seeing you, I'm seeing my window, et cetera, et cetera. And simultaneously, my world is observing me, if you will. So I'm moving around, I'm radiating heat, I'm breathing, I'm doing things that affect the state of the world. So there's this exchange. That's a physical interaction.
Right.
But that physical interaction moves information back and forth.
Right. Okay. So to back up a little bit, I just want to make sure I understand what you're saying. So a system, I mean, if we talk about the two entangled particles, then they're obviously, one system, because they cannot be independently sort of changed without impacting each other. So sort of a definition of system is where you can independently change something without impacting the other thing in a significant manner. And if we see universe as a whole, say from a vantage point of somewhere on the outside, even though it's not possible, then quantum theory says everything is entangled. So there is no sort of clear system that can be identified from the outside. But within it, are you saying for practical purposes, we can assume isolated systems exist and they are making observations?
Well, there are several pieces of that, so let's distinguish them. For practical purposes, we have to be able to say that systems exist, because for practical purposes, if we're going to do experiments, we have to say that we exist, and we have to say that our measurement apparatus exists, and we have to say that we're embedded in some environment that we don't care about. So those, if we're going to talk about anything at all, we have to make those kinds of assumptions. Now, those systems aren't isolated, because there's only something interesting to say if those systems are exchanging information with each other. So they're not isolated, but they're interacting fairly weakly. They're interacting weakly enough that the overall evolution of the universe doesn't re-entangle them in the amount of time that's interesting.
Okay.
So if you take a system, take the universe, right, decompose it in two, and say, okay, I have my two weakly interacting systems that I can talk about a separable state, but I leave that for a long time. If I just let it sit there and let the two systems interact, eventually they'll become entangled again. Mm-hmm. That's just what quantum theory demands, right? The whole system is isolated, so it's a unitary propagator, so it's going to re-entangle everything. So in a sense, our observations have to be fast on some time scale. So from a practical point of view, you can think of our conversation is happening very quickly on the time scale of the evolution of the universe, right? So it's effectively instantaneous.
Right.
So we don't have to worry about our separability assumption breaking down, the assumption that we have to make to have a conversation in the first place, or to record data in a notebook or to do anything else. We don't have to worry about that assumption breaking down because we're doing things very quickly.
Right. So what does exchange of information mean? I mean, I understand that from the human context, we are speaking things and you're understanding what I'm saying. But say from a non-human system perspective, what does exchange of information mean?
Well, I think we can ask that question at different levels of anthropomorphism, because again, we're relying on our intuitions about what these words mean. And this is a place where thinking about biology is very useful. So you can think about animals communicating in the wild, and that's pretty clearly like human communication, right? So meerkat gives an alarm call and the other meerkats do something or other in response. So this is communication in a way that we can really understand from our human perspective. But we can take that sense of communication to plants or to microorganisms, and it still works pretty well. So if you're thinking about human physiology, certainly if you're thinking about neuroscience, it's very natural to talk about nerves communicating with each other, or nerves communicating with muscle, for example, or immune system cells communicating with each other. So this idea of information exchange is actually very natural throughout biology. And biologists have been using this way of talking for decades now. So it's very standard. And some people still kind of object to it as being not quite scientific. But it's not only useful as a language, but it's useful quantitatively to be able to talk about exactly how many bits are being exchanged. And once you are quantitative in terms of bits, you can be quantitative in terms of energy use and things like that. So there are things that one can measure in consequence of making claims about information.
Yeah.
So now go down to the molecular scale. If you think about something like DNA binding a protein, you can look at the DNA sequence that binds this particular protein and ask how many bits of information are encoded in this binding site. And if you have one protein and it binds many different places on the DNA, then you line them all up and you do the statistics on what nucleotides are present in what position, and you can work out the information content of that binding site. So again, this is a quantitative idea of information transfer between two molecules. So one can take that farther and think about a particle exchanging information about its position with a field or something like that. And perhaps it becomes less useful there because there's no longer the good quantitation to be done. But if you think about reactions in particle physics as flipping bits, then a scattering process may be thought of as just an elementary information exchange.
Yeah. Yeah, that's what I was imagining. Say a photon interacts with an electron in an atom, and the electron goes to some energy level, and the photon's say momentum changes because of interaction. So, are you suggesting they are in some sense exchanging information
Yeah,
about each other?
right.
Interesting. So, where does I mean we know from experiments that outcomes in quantum theory are probabilistic. So the electron can go to uh, any sort of energy level. I mean, it's not defined. It will only go to a specific energy level. So what does information mean in that sense when there is uncertainty of what sort of information is getting exchanged? I mean, in our sense, human context, I'm not sure there is so much of uncertainty, but I mean, I'm just trying to understand, is in a very crude sense, do we say measurement problem is really a way of looking at what information different systems choose to reveal, for lack of a better word?
Yes, and I think your question, it opens up a deep debate in the philosophy of mathematics that has to do with what is the nature of probability. And the two sides of the debate are objectivists about probability, who believe that probabilities are, if you will, real ontological features of the universe, and subjectivists about probabilities that believe that probabilities are always descriptions of a point of view. And the Bayesian tradition is based on this subjectivist notion of probability. And it's certainly the version that I can make sense of. So if we view probabilities in this subjectivist way, then an event is probabilistic always with respect to some observational process that has to be specified. So suppose I want to measure the spin of an electron. Then the first thing that I have to do is find an electron. And then I measure its spin. And I may say the probability of my measurement is half and half, spin up or spin down. Well, what does that mean? And certainly from this subjectivist point of view, it means before I made the measurement, I was uncertain about whether the spin was up and down. But notice that I was certain about something. I was certain about I'm measuring an electron. That's a baseline assumption that I've made. There's no uncertainty about the fact that this thing I'm looking at is an electron, not a proton or something else. So I'm measuring the spin of an electron. But I'm uncertain about what the outcome is going to be until I get it. And then I know exactly what it was. So I updated my probabilities about the electron spin after I've made the measurement. So what does that say about the electron spin kind of in reality? And a pure subjectivist would say it doesn't say anything about the electron spin in reality. Right? The electron is there, we can assume. But it was a physical process acting on the electron that allowed me to capture the thing so that I could measure its spin. And I don't have a description of that capturing process in my description of measuring its spin. I assume that it's already captured. I've acted on this electron with the Z-spin operator, but the Z-spin operator is acting on the electron. I haven't described the capturing process. So this is a description that by and large is missing in physics when we talk about measurement. The description of how we localize and identify the system that we're measuring. And it's simply taken for granted that we can do that.
Right.
So here's a fable, right? You have a brand new student who's never been in your laboratory before, and you say, go into the lab over there and tell me what the Keithley voltmeter is reading. And so the student walks into the lab, and there's this bewildering array of instruments and wires and flashing lights and goodness knows what. So what does the student need to know before she can make the measurement of the reading on the voltmeter? She needs to know how to find the voltmeter.
Yeah.
She needs to know what a voltmeter is and how to identify one, and what the word Keithley means, and things like that. So there's a lot of knowledge, and hence a lot of observational work that goes into identifying a system. And if we really want a complete description of measurement as an interaction between me and my world, we have to include the description of how I pick out the systems in the world and what measurements I have to make to identify my laptop, to identify my water bottle, to identify my cell phone, to distinguish all the things that I distinguish perfectly naturally. And to neglect that is to actually neglect most of my interaction with the world.
So, I'm just trying to again capture what you've said. Are you trying to sort of suggest that the so-called measurement problem, where experimental outcomes are probabilistic, they perhaps have to do with maybe not specifying the system, not having knowledge of what system you're going to interact with, and the experimental outcomes make that clear? I mean, because I'm trying to understand, if you've put boundaries and identified a system, why should I agree that that is a prerequisite, knowing what system you are measuring. But after you've done that, why should outcomes be probabilistic?
Okay. I think one needs to ask, what is probabilistic? What are you uncertain about? So
yeah,
if I'm walking up to an instrument, and we'll use the standard terminology of an instrument that has a dial with a needle. So we talk about the pointer state of an instrument. That's how is the pointer pointing in the dial? So I walk up to the instrument, and I don't look at its pointer state, but I identify it. So I said, this is the thing I have to make a measurement of.
Yeah.
This is the thing that I'm going to use to make a measurement. And I'm making a measurement because there's something I don't know. Otherwise, I wouldn't bother.
Yeah.
So because there's something I don't know, my understanding of the world is already probabilistic. If I know nothing whatsoever about what my instrument's connected to, I know nothing at all about what the pointer will be reading in its dial. So I can say, oh, my probabilities for the pointer position are uniform, my prior probabilities. I haven't made an observation of it. And I'm making an observation in order to find that out, in order to decrease that uncertainty. So I make the observation. Now I know the pointer is pointing to 5. So I can describe that as the collapse of the wave function if I want to, right? Although that seems an overly dramatic language to use for resolving my uncertainty about the position of the pointer. So what does that say about the state of whatever that meter is connected to? And I would say it doesn't say anything about the prior state. Right? I was the one who was uncertain. I made the measurement. Now I know the measurement outcome is 5. Was the state of the system uncertain beforehand? That question doesn't even make sense.
Yeah.
Right? I was uncertain.
Yeah. I think I understand what you're trying to say. This is a consequence of importing intuitions from the classical world, where you can specify, say, position, momentum to a very good precision, and you can apply laws, and it assumes that you know the state to a good degree, but in the real world, you perhaps may not know in the first place. So when you make a measurement, it appears probabilistic, but it's a function of lack of being able to specify the state.
Yeah, I'm in a sense making an argument that Chris Fuchs has made very well, and his colleagues in developing quantum Bayesianism, or what's now called cubism.
Yeah.
And beginning in 2010, at any rate. So he spent a decade doing this, and his papers are very well worth reading. But he makes the point very plainly that when we talk about uncertainty, we have to ask, whose uncertainty is it? And how is that uncertainty resolved? And to what extent is it resolved?
Right. Yeah. But I guess, but
you're right that we do come at this with classical intuitions, and those intuitions are in a large part driven by this classical notion of a perfectly objective point of view. So if we think about a classical ideal gas contained in a container, then classically we have an ensemble of velocities and positions at any instant. And so we regard that as random. But what does that actually mean, right? We think of this global kind of God's eye perspective that could actually know, this gas molecule is moving this way, this one over here is moving that way, and this one is doing this, and we can't see any of that. So we think they're random. But each gas molecule is actually moving in some single direction from some single position in classical physics. That's what we imagine. And quantum theory, in a sense, allows us to do away with that assumption. So we don't have to make that assumption. We can just talk about what we actually see. What are the experimental outcomes that we actually get? And what is our uncertainty before we make a measurement and what's our uncertainty after we make a measurement.
Right. I mean, this. I mean, it's pointing to the fact that whatever reality is, it's perhaps unknowable, but then it also sort of contrasts with a lot of quantum phenomena. I mean, most of the quantum phenomena following these statistical laws. I mean, if you perform an experiment again and again, you could predict where things will line up. So, I mean, did you see these two things challenging each other? Because if there is this uncertainty, then why do we have these meta laws at all?
Well, think about things that we know very well, like the magnetic moment of the electron or something like that. Right? We can measure it over and over and over again, and we get these numbers that we can predict and agree about to 10 or 12 or 14 significant figures. So there's certainly some regularity in the world that we're measuring. And if we look at the world in a very specific way, then we can have extremely high confidence that we're going to get this answer, because there's some regularity or other about the world that we're probing, and we call that regularity the magnetic moment of the electron. And we have a picture in our head of what that means. Actually, we have many different pictures in our heads about what that means. Right? We have the picture of the electron as a little particle that with a spin. We have the picture of the electron as an excitation in a field that permeates space-time. We have these different pictures, which we can manipulate mathematically to come up with a value for this regularity. So the regularity is incredibly useful. We know how to use it to manipulate the world. So we know how to use it to act on the world. But it doesn't demand of us any particular metaphysics. Right? We can view it as a phenomenon that we know how to produce by acting on the world in a particular way.
Yeah. I mean, again, I mean, for example, from a subjectivist point of view, if you're doing the double-slit experiment, it's impossible to predict where a particular electron will land up in the pattern, but you can very well predict a pattern will emerge if you do the double-slit experiment number of times. So isn't the existence of that pattern in double-slit experiment an indicator of some sort of objectivity in the world? So doesn't that undermine a little bit the subjectivist point of view?
I don't think it undermines the subjectivist point of view about probabilities. Again, I at least would not advocate a position that says that there are no regularities in the universe at all. There are clearly regularities in the universe, or in, to, I think, put it more precisely, there's certainly regularities in our interactions with the universe. And the double-slit experiment is one of them. So the double-slit experiment is certainly telling us something very important. It tells us that our classical notion of what a particle is wrong, for example.
Yeah.
It's not applicable to how the world actually behaves. So it's giving us real information. I think we just have to be very careful in saying, what information is it giving us? What are we really learning here from this regularity in the world that we know we can observe if we do certain things?
Right. So you said something very interesting. You said double-slit experiment is a feature of our interaction of the world and not necessarily an objective feature of the world, say independent of us per se. So, and I know you've talked about and written about how sort of maybe it's almost impossible to talk about a completely observer-free objective world out there. So can you elaborate on that? Why did you have to specify it's a feature of our world?
Okay. Yes, I can do that. And it goes back to the very first thing we talked about when we talked about having a universe that's described by quantum theory that is sitting there effectively letting its phase rotate around its Hilbert space. And we divided that universe into two. And we talked about information exchange between the two. Now, prior to that division, there's no classical information in that system at all. There's no place to put it. Right? All we have is a state vector in Hilbert space. Once we make the division, we can talk about an interaction between the two parts. And we can talk about the eigenvalues of that interaction, which are just numbers. So that's classical information. And we can ask, where is that classical information? And the holographic principle actually gives us the answer. The classical information is encoded on the boundary. And it's encoded at there's a maximal density of encoding that defines the smallest possible voxel of space. And it's very small, so you can actually get a lot of information on the boundary. But that's where it is. That's where the classical information is. So let's go back to your question about objectivity and why I think we always have to talk about observations as relative to an observer. If we think about observational outcomes as classical information, then they're encoded someplace. And the basic physics would say they're encoded on the boundary between the system that we're calling the observer and the system that we're calling what's being observed. So now it's logically impossible for them not to be observer relative. So if I'm going to draw this universe in the air with my hands, right? Here it is.
And,
okay.
And Dr. Fields, for the benefit of listeners who may not be very familiar with, and I know it may be hard, but when you say nothing ever happens in the universe as a whole, I mean, how do you sort of explain that? Because I'm not sure if everyone would understand what a Hilbert space is or a vector is. Maybe some analogy to understand that classical information can only exist at a boundary.
Okay. This is a good question, and the image I have in my mind is from Tina Weymouth of the Talking Heads playing the song "Heaven is the place where nothing ever happens." A Hilbert space by itself is a place where nothing ever happens. So what's a Hilbert space? A Hilbert space is a vector space. It's an abstract mathematical object. And if you think of a system as having what physicists call degrees of freedom, which means characteristics that can vary in some way or other. Then you take all the degrees of freedom and you take all the ways that they can vary, and every single distinct possible configuration of degrees of freedom having values, you assign a vector to.
Okay.
And you put all of those vectors into a big abstract space with enormous dimensionality.
Right.
And that's a Hilbert space. And so if you want to say, what's the state of the entire system, then it's some vector in that space, because that's the way you've defined the space. It's the space of all possibilities. And if you think of what's that system doing, it's just exploring the possibilities in its space of possibilities. So its state is some vector that's migrating around in that space of possibilities. And that migration process has a description in quantum theory, which is called unitary evolution. And what that means is no information is lost in this evolution.
So
no information is gained either.
It's sort of like a clockwork, deterministic.
Yeah, it's actually very much like the concept of Laplace, when everything affected everything else instantaneously.
Right. So there are no probabilities involved. What's going to happen from a instance to instance is completely determined by the previous state.
It's determined by the evolution itself. And this whole picture becomes intuitively, it's very difficult to keep in your mind, because when we think of a system evolving, we think of it as evolving in time, but there's no clock. There's no external clock. There's just this universe. So if there are any clocks, the clocks are on the inside, and their states are part of the migration of the state vector.
Interesting.
So we can't really bring these intuitions about time into thinking about a universe using quantum theory.
Got it. So what you were saying was there is no information to be gained because no information is lost. So there's no uncertainty. And when we talk about observation, which is always about uncertainty reduction, then the reason it's classical is because at the whole universe scale, there is no observation to be made.
Right. Yeah. To talk about observation, you have to cut the universe in two.
Okay. And again, what did you mean when you said this information exists at a boundary?
So if you think of, you've got your universe, right? You slice it in two. So you've got the left half, call it A, and the right half, call it B, and they're interacting. And so you can ask, how big is this interaction compared to the sizes of A and B? Well, remember, previously we were talking about this assumption that we have to make that the interaction is weak.
Yeah. In
order for A and B to have well-defined states. So if the interaction is weak, it means that the area, if you will, there's no space-time here yet, right? The area, if you will, where the interaction is taking place is kind of small with respect to the whole degrees of freedom of A and B.
Okay.
They're just interacting a little bit. So you can think of that interaction, and here we'll actually think about little spinning things. right? That interaction has a particular dimensionality, which is given by how many degrees of freedom are involved in actually interacting.
Right.
How many degrees of freedom are touching each other, if you will. And that dimensionality can be represented mathematically when we write down the interaction. And one can always represent that interaction mathematically by assuming that what the systems are doing is exchanging bits. And if you want to think of it, you can imagine that they have a whole string of quantum bits, of little spins. And what the system A does is arrange those spins in some particular pattern, up, down, up, down, up, down, up, down. And system A has her own idea of what up means and what down means. And then system B over here looks at those spins and makes measurements. And system B has its own idea of what up is and what down is. A and B are different, so they can have completely different ideas. So if A says, okay, spin number one is up this way, but up for B is this way.
Right.
Then when B, using this direction for up, measures this spin, it's perpendicular. So its probabilities are going to be the same, one way or the other. But if B happens to think that up is this way, then it will get the value 1 all the time.
Right.
So you can think of these systems as exchanging bits, but with an uncertainty. The uncertainty is based on their possible disagreement about what they mean by up.
Right. Yeah. I mean, the uncertainty is in lack of shared vocabulary or
Right.
incomplete overlap.
Yeah. And you've cut the system in two. This is their only communication, is arranging these bits.
Right.
So there's no prior agreement about what counts as up. So the holographic principle is just the idea that we can always represent this kind of encoding of information as encoded on a surface at a particular scale. And that principle comes from black hole physics and as a way of talking about how much information can be obtained from a black hole by someone looking at it from the outside. And it's exactly proportional to the surface area, not to the volume. Hence the idea of holography. But it's also clear if you just think about it in this more abstract way of two systems exchanging information. We've made the assumption that, that the interaction is weak. So the systems don't know much about each other. They just know what's encodable on this shared sequence of bits or shared little holographic screen that they're writing bits on.
Right. I mean, it sort of reminds me of how, say, something like cryptography works, where there is this exchange of information, but through a channel, and you have to define the protocol first. Otherwise, nothing makes sense.
Right. Exactly. I mean, it applies to any communication set.
Right. Right. So, Dr. Field, since we are coming to the end of our conversation, I wanted to sort of just explore as a last bit, how does this all connect to panpsychism? I know in one of the talks, you mentioned that you feel it's inevitable feature. Panpsychism is where consciousness or this experience is a feature of the universe. So can you talk about how did you arrive at that view, if I'm capturing it correctly?
I would say that if one thinks about observation and measurement in this way that we've just been describing, then that description is completely independent of what the systems we're talking about are. It's completely independent of how we've sliced the universe up. So if it describes us and our obtaining of information from the world, then it describes how trees obtain information from the world, and it describes how electrons obtain information from the world, and how planets obtain information from the world. It doesn't matter. It's any system. So it's not just scale independent, but it's independent of everything else as well. So if one thinks about our experiences, which I do, as the outcomes of our observation, our observing actions on the world, then we have a ready-made theory for how that works. It's quantum information theory, and it applies to everything. So I think that's at least a good starting point for saying what's true of my experience is true of experience in general. And hence a good starting point for thinking, okay, well, you certainly see biological systems at all scales exchanging information. And we certainly see that information exchange affecting behavior in very important ways. And we see biological systems at all scales having experiences that, or having observations, shall we say, that they like and they don't like, that they approach to get more of and run away from to get less of, even in plants, certainly in bacteria. So why not regard this as experience? I think it's perfectly reasonable to regard it as experience.
Yeah.
And if you're willing to go to the molecular scale, then you might as well go to arbitrary scales.
Yeah. And the consequence of this are baffling.
Yes.
Have you seen any change in your personal beliefs or the way you live because of these conclusions?
Well, I've probably always had a fairly panpsychist outlook. I would say I've probably become a nicer person in the last 10 years since I started meditating. But I don't have a good answer to that question, actually.
Yeah. Great. So thank you so much, Dr. Chris Fields. It's been an absolute pleasure to talk to you. I mean, I thoroughly enjoyed it. I have lots of more threads to explore, but in a limited time, I think we've gotten a lot of key points sorted out. At least I've gotten them sorted out. And I think this idea of nothing ever happens in the universe and the information being limited to what two systems, for lack of a better word, choose to exchange is deeply fascinating, because beyond the observation, there is no way to say what must be happening in the true objective world. Maybe an electron is not an electron as we see it, but that's just the interface we have with the world.
No, I think that's a good summary. Well, thank you very much.
Thank you. Have a great day. Bye-bye.
Thanks.
Take care.
Cheers.
Cheers.